What is common between the Channel Tunnel, the Great Pyramid of Egypt, and the Eupalinian Aqueduct? Nothing simpler than an isosceles triangle. This sounds confusing without some explanation. We do know that for any two given points A and B that exist in three-dimensional space, only one straight line exists that passes through both points. But what if an obstacle existed, or it was needed to move to a point C for a certain reason and then go to point B? Which position should point C have, so our calculations would be easy? The answer to that is the isosceles triangle. From theory we know that an isosceles triangle has two equal corners and one supplementary of those two, so that the sum of all angles is 180 degrees. The angle at point A is theta degrees, then the angle at point B is also theta degrees. This makes the angle at point C to be 180 degrees minus 2 times theta. All that make us to understand that the supplementary angle of point C will be 2 times theta. We also do know that in an isosceles triangle sides AC and CB are equal. This simple solution in our two-dimensional example is provided by two isosceles triangles. The upper one as we see it and the lower one, providing two possible paths. The isosceles triangle method practically means that if someone was standing at point A, made a turn left of theta degrees and moved at a distance of x meters and stop, that would be point C. In order from point C to reach point B, all that would be needed is to turn right, for an angle of 2 times theta, and walk another x meters. So how this have to do with the Channel Tunnel, the Great Pyramid of Giza, and the Eupalinian Aqueduct? Let's start with an image of the route of the Channel Tunnel from Wikipedia. You still do not see the isosceles triangle? Now it is easier to understand it. Time for the Great Pyramid of Giza. And more specially, the Queen's Chamber Airshafts. We can see that there is a zigzag here, which actually is an isosceles triangle. They used this technique to avoid something but still be on the same line they started. It gets better at the Queen's Chamber. The air shaft appears to have multiple zigzags. But if you look closer you will understand that it is two isosceles triangles. The second starts at the point the first ends. This gives this peculiar look of a zigzag. This technique had a liftoff at the construction of the Eupalinian Aqueduct. It was used so much, and as we see the path of the tunnel from above, it gives the feeling to the viewer of having random zigzags. But in fact it is full of isosceles triangles used as sets of 2 or 3. For example, starting from the north side, the first zigzag has a starting side that is made of 2 other merged isosceles triangles. As you understand, the method is very easy. And ease of use is the reason that it is vastly used throughout the years. Thank you for watching.